Hello! Today the topic of our lecture is multi-material modeling. At the present moment, computer-aided design and computational material science have reached a point where heterogeneous volume modeling and volume cut systems are required. First of all, let's define the terms. We will consider object shapes as geometric point set, volumetric material distribution as non-uniform gradually varying materials, multiscale microstructures as internal spatial geometric structures with size of details orders of magnitude smaller than the overall size of the object. As we remember, the constructive hypervolume model was proposed for modeling heterogeneous objects using function representation approach. Heterogeneous materials can be found in nature, as example, geology. The three types of multi-material objects are presented on this slide. It's multiple homogeneous materials, composite material, and functionally great material. Here is an example of sliced patterns of heterogeneous object. Material modeling with scalar fields includes following items. It's analytical, sampled, simulation and optimization, spline-based, source-based, feature-based, shape-conforming, compound and constructive, and procedural. Source-based methods allow users to specify information regarding attributes inside the shape by defining the sources for material distributions and procedures to find the values of the attributes in the ambiguous areas where no source has been set up. In this method, material sources with single uniform material are introduced. These material sources are assigned with distance fields such as points, lines, or outer surface boundaries, and apply some interpolation to define material at any point. In material grading, the material composition of an object varies from one end composition to another, which are stored in the material composition arrays MS and ME. The both ends connect by the material grading function. MSG is ith element of the material composition. The sum of all elements of material composition is equal to 1. The material grading function f of d is a function of distance from geometric point to reference datum, which are termed as grading source. The reference could be a fixed reference in the coordinate system of the model, such as a point, a line, a plane, or the outermost boundaries of a model. Grading function f of d can be either linear or non-linear mathematical function. Figures in the bottom of the slide show effects of grading using grading functions. Figure A is material grading using a non-linear function. Figure B is material grading using a linear function. In the example, the three materials are represented in material composition. Grading sources can be a point, a line, a plane, or the outermost boundaries. Examples are shown on this slide. Here you can see a graph of the volume fraction versus the radial distance for a material composition consisting of three materials. Next approach is feature-based material modeling. In this method, we introduce material features with single uniform material, represent material features with scalar fields or obtain smooth approximation of distance fields. Apply the transfinite interpolation to define material at any point. The weight functions are used for calculation influence of each material function in the point P. The weight summation of the materials participating for the given point is used. Here is an example of the feature-based gradient volumetric materials. The next approach is procedural volumetric materials. Shape-aware material distribution method is interpolation material properties and attributes based on the accessibility of the points with respect to the material features defined by the users. This method requires the non-overlapping source features with constant material to interpolate gradient materials by using Voronoi diagrams on interior distances. Interior or inner distance measures the path between two points inside the object, where all the points of the path belong to the interior or the surface of the object. The use of internal distances is a good way to take the shape of the volume object into account while interpolating the material attributes in the areas where the material is not defined. This method allows for the definition of material sources as geometric objects defined by continuous scalar fields, and therefore by using internal distances and Voronoi diagrams together achieve intuitive results to the user. In this example, the four features were used for control the attributes of the form structure, which are average cell size, wall thickness, and roundness. So, after using interpolation, the scalar fields influenced to the result shape parameters were obtained. The large red feature uses a small cell size, large blended value, and thick walls. The green feature contrasts with narrow walls, practically no blending, and ample cell size. The last two features, yellow and blue, have high blending and thick walls. Multi-material surface discretization is presented as algorithm for meshing implicit surfaces based on the Delaunay triangulation of a point set adaptively sampled on an implicit surface. This algorithm consists of three steps. Its adaptively discretized surface for all material regions. Define and sample the boundary curves between each pair of materials. And assembly meshes together while protecting the material boundary curves. Let's look at these steps in more detail. Surface discretization for space partitioning starts from generation random points and project them on the surface, then adding ghost points from the bounding box. Compute the Delaunay tetralization of the obtained point set. Find the set of triangles on the surface. Subdivide triangles with high surface curvature and optimize the mesh. Here are examples of surface discretization. The second step is to determine the material boundary curves. Step number 3 is assembly of meshes and boundary curves. The final step is mesh optimization. These are examples of polygonization of multi-material objects. Now let's consider direct manufacturing. Direct manufacturing is the fabrication of models without an intermediate format. This approach translates the 3D model into commands of the numerical controlled machine, in our case 3D printers. FREP-CAM is computer-aided manufacturing system for 3D printing of functionally presented models directly. It allows to slice FREP models and get a set of layers for 3D printing. As example of multi-material direct 3D printing is Geological Model, which was modeled using Hyperfun software. And this model was fabricated using 3D printer Z Corp. Another example is multi-material helmet and multi-material corset.